In this video, I introduce deep reinforcement learning from human preferences. Reinforcement learning requires a predefined reward function. However, many tasks involve goals that are hard to predefine reward functions. Given demonstrations of the desired task, inverse reinforcement learning constructs a reward function. The extracted reward function can then be used to train a reinforcement learning agent, namely using admission learning to clone the demonstrated behavior. However, this approach is not applicable to behaviors that are difficult for humans to demonstrate. Deep reinforcement learning agent learns a policy with human preferences through a reward prediction trained by human feedback in the supervised manner, as shown here. The deep reinforcement learning model is trained to optimize the predicted reward by using the reward from the reward model as a target reward. In this way, the policy optimized by a deep reinforcement learning model can generate outputs aligning to human preferences. The reinforcement learning policy and the reward predictor are trained asynchronously. At each time D, the agent observes the observation OT from his environment, sends action AT to the environment, and then receives the reward RT. The goal is to maximize the discounted sum of rewards and aligns the generated policy with the human preferences. The model consists of one policy network pi and one reward network, as shown here and here. First, the policy pi interacts with the environment to produce a set of trajectories from tau 1 to tau I. The policy network is updated by reinforcement learning to maximize the sum of the rewards RT, as shown here. Select a trajectory pair, sigma 1 and sigma 2, from the trajectory set for human comparison. The reward network R caret is optimized via supervised learning to fit the comparisons collected from the human so far. This is the workflow of the deep reinforcement learning from human preferences. Suppose that the human probability of preferring a trajectory segment sigma I depends exponentially on the value of the latent reward summed over the length of the segment, as shown here. The reward model minimizes the cross-entropy loss between the predictions and the actual human labels, defined as here, which estimates the probability that one trajectory segment is preferred than another trajectory segment. For more details, please check with these references. Thank you. Bye.